So last time we did the lune of Hippocrates. Hippocrates' quadrature of the lune. So we had an isosceles right triangle. And Hippocrates says, the same isosceles right triangle that we keep coming back to again and again. And Hippocrates says, if you draw this semicircle and you draw this semicircle, the two create a lune. And then we proved that that lune has the same area as the half of the isosceles triangle. And so because those two areas are the same and triangles are quadruple, so is the lune. Right? Ring a bell? Then we went to the big three. There are others, but these are sort of the big three construction problems from antiquity. Construction problems from antiquity. Do we remember what they were? Yes? Marley.
So I'll give the last two. W cube in squaring a circle and try something in angle.
Yes. Yes, exactly. So the way we got to this is people thought that if you could do this lune, then you could do other lunes. And if you could do other lunes, then you could square a circle. So squaring the circle, square the circle, or quadrature of the circle, same thing. That's one of the construction problems from antiquity. So let's just write them down and then we'll go into them one by one. The second, Marley, doubling a cube. Doubling a cube. And the third one, they're in no particular order. Trisecting, yeah, trisecting an angle. Trisecting an angle. So let's just go into these with a little bit more detail. So squaring a circle, what does that mean? We're given a circle. And the question is, can we construct, let's see, let me try to not make you read my chicken scratch. Can we construct a square with exactly, as always, exactly the same area? And it's clear that such a square exists, right? Clearly, such a square exists. That's not the question. Why is it clear that such a square exists? Well, you have your circle, and that circle is contained inside the circumscribed. That circle is inscribed in a square. So that square obviously has a larger area. There's also the inscribed square, the square inscribed in the circle. That square has a smaller area than the circle. So somewhere in between, there's some Goldilocks zone. Somewhere in between is going to be a square that's not quite inscribed and not quite circumscribed, and it has exactly the same area as the circle. And the question is to find it, construct it somehow. So what is the area of the circle? As we all know, pi r squared. Let's make life simple. Suppose that the radius is 1. So we have a unit circle. Then the area is just pi. And so to construct a square with exactly the same area is the same thing. So let's write this down. So to construct a square with exactly the same area amounts to constructing a length of what? If you want to, if you can construct a square, then you can construct a length, which is the what of the area of the square? Somebody said it. Square root, right? So if you can construct a square root of pi by square root of pi square, in other words, if you can construct a length of square root of pi, if that length can be made root pi, then the area of the square will be root pi by root pi, also known as pi. So that's what we want. The question is, can you construct? So the real question becomes, the main question becomes, can you construct a length of square root of pi? That's the mystery. How do you do it? I'm not going to answer that question right now. Well, I already told you the answer. What's the answer? How do you do it? You can't. You can't do it. You can't do it when construct means with straight edge and compass. Obviously, it exists. That's not the question. How do you construct it? The answer is you can't. But let's do one. Let's see why you might think that some of these problems are solvable. Let's go to number 3. So here's a solution to number 3. Number 3, trisecting an angle. What does that mean, trisecting an angle? Well, there's something you probably learned in school called bisecting an angle. What is bisecting an angle? Splitting it into 2 parts, exactly, an angle. Does anybody remember how you do this? If you're given some angle, let's say OA, you remember how to bisect it? Let's try. So if we have a let's make a ray. I think that'll look a little nicer. So if we have some angle here, an angle from B to A to C, okay? So this is some angle. This is telling me it's 52 degrees, whatever. Can you see that? Yeah. So there's some angle. And I want to make an angle that's exactly half of that. Anybody remember how we do this? It's okay if not. Laurie, you got an idea?
I don't remember exactly the details, but you use the compass with point A as the circle.
Love it.
And you do arcs which are going to intersect.
Yes.
When you bisect the angle.
Exactly right. Exactly right.
Radius by having a fixed radius, but from slightly different points. Is that it?
You're almost there. You're almost there. There's one thing I want to point out. You see how I misclicked a little bit and the point D, can you see that that's a light blue? So I forgot to tell you what the color scheme means in GeoGebra. Some of you I noticed we're struggling with this. Blue means it's totally free. I can drag this point wherever it's not required to do anything. Light blue means it's somewhat restricted. This point D is, it correctly understood when I clicked to mean that that point D needs to be on the line, but it did not understand that I want it also to be on the circle. And so let's undo this point. Oh, it's going to undo all the motion first. Okay. And now I want to place a point at the intersection. And there. Now it's black. And black means there's nothing I can do to that. I can't pull that point around. GeoGebra has understood that that point needs to be on the line and needs to be on the circle. It has no degrees of freedom. Okay. So light blue is a little bit of freedom. Dark blue is you have complete freedom, and the rest of the picture will adjust accordingly. And black means that point's not going anywhere. So what Laurie said is that now this point D and B, these 2 points we've made some kind of isosceles triangle because these are both radii. The triangle A to D to B is isosceles. So if we drop an altitude to that triangle, that'll exactly bisect the angle. Everybody see that? Let's just see how to do it, and then we'll write it all down carefully. So the way to drop an altitude is just to get a perpendicular bisector. In fact, angle bisector is already one of the tools. Angle bisector is not a tool that you get with straight edge and compass. It's something that you can do, and so GeoGebra allows you to skip the steps. But if you couldn't skip the steps, how would you do it? You could draw a circle from B to D, and another circle from D to B. And those 2 circles meet at 2 points. One point is here. No, I missed because it's not black. Please, pretty please. Let me slide this around a little bit so that, yeah, now I have a little bit of distance because I think GeoGebra is not understanding which point I mean. That's the point I want. And then this is the other point of intersection right there. And a line through those 2 points, E and F, will go through A, and in fact will be exactly half of the angle. So let's see the angle from F to A to B, and I can't see that. Yeah, the big angle is 70. Oh, whoops, I misclicked. Allison, question?
But could you, if you did want to draw the circles, could you draw a line from B to B?
Yes. Yes. So exactly right. We can draw the line from D to B, and then we can find the midpoint. But how do you find the midpoint? There's, again, the midpoint isn't, it's a tool that GeoGebra gives us because there's an algorithm for computing it. It's saving us a bunch of steps. But the algorithm for computing that midpoint is exactly the one that we just went over. So we went really back to basics with only straight edge and compass. But you're exactly right that that midpoint accomplishes the same thing. If we measure this angle, I say I'm supposed to measure it from B to A to wherever F, anything on this line will do. And hopefully you see that this angle is 35 as opposed to 70. It's exactly half the angle. Does that make sense? Let's go over that. We went over that very quickly. I just wanted to show you what the construction is. Let's go over the construction. Yeah? You guys are asleep. Alexander.
Circles, can we use the midpoint tool?
You can use the midpoint tool. You can use the midpoint tool. I might ask, how do you construct a midpoint? And if I ask that, then the answer isn't, well, you just click the midpoint tool and it does it for you. It's exactly this operation. This is like the only operation that there is, by the way. If you've been following along, like anytime we want to do something, drop a perpendicular, it's draw 2 circles. That'll give you a perpendicular. Get a midpoint, draw 2 circles. That'll give you the midpoint. Bisect an angle, draw 2 circles. That'll give you the bisector. Well, there are 2 points of intersection, and those 2 points of intersection determine a line, and that line will be the angled bisector. It'll be the perpendicular bisector. It'll also give you the midpoint. It accomplishes all those tasks at once, which is why GeoGebra says, don't bother drawing all these circles. I'll just let you put the midpoint there. I trust that you know how to do it. Okay, does that make sense? In the same way that there is also a tool that allows you to just construct the angle bisector without doing the time. Is that a question, Alicia? No. Okay, so let's go over the process. Step 1, I'm just reminding you this is some of you saw this in grade school. So draw a circle with a center at O and radius OA. Okay, so I'm just going to draw a circle because I want this point. What was this point called something else, or should we just call it B? Do you care? What do you want to call this point? Layla, what do you want to call this point? B, great. I agree. Let's call that point B. Notice, this isn't part of the construction. This is just like, why are we doing this? Notice that triangle AOB is isosceles. Danny, did you say that? Somebody said it. You didn't say it? Okay, somebody said it. I heard, maybe voices are appearing in my mind. Is isosceles. So really what we want to do is drop an altitude to that triangle, which means construct a perpendicular through O. There's a variety of ways of doing that. So now, well, if you want, just get the midpoint. If you allow me to say get the midpoint, but how do you get the midpoint? So let's remember how to get the midpoint. So step 2 is want the midpoint from A to B. But how do you do that? Well, you can draw a circle with center A and radius AB. So there's one circle like this. I'm just going to draw a little bit of it. And then next step is draw another circle with center B and also the same radius AB. So centered here, the radius is AB. That gives us 2 points of intersection. Should we give these points names? No, Layla, no name. Yeah, they're not worth giving names to. And then draw a line. Okay, this is step 4. Draw a line through those 2 points of intersection. Okay, so we have these 2 points. We constructed these 2 new points. We draw a line through these 2 points of intersection. It will pass through O. And the claim is that that line is the angle bisector. Then that line is the angle bisector. And that's just by symmetry. I didn't draw it very well, but the picture is completely symmetric across that line. Alicia.
So if I see what you've done with bisecting line, would you see B to A?
There's a dotted curve from B to A, which was the first circle, which was only to get me the point B in the first place. That gives me the point B. This gives me the point B, so that OB is the same as AB, is the same as OA, to get me that isosceles triangle. Once I have an isosceles triangle, I cut it in half, and so I've halved the angle at O. Does that make sense? Let me show you how to trisect an angle. That's the right response. Okay, claim. Here is how to trisect an angle. Here is how to cut an angle into 3, not into 2. Trisect an angle. Okay, so again, we're given an angle. Let's call this O. Let's call this point A. And I have some other line over there. Okay, so we're given an angle. Given an angle at O. I'll call that angle alpha. Alpha. Well, bisecting, there's no problem. Bisecting, here's the process. Bisecting an angle we can do with straightedge and compass. The question is, can we cut an angle into 3 equal parts, not 2 equal parts? If you can cut it in 2, then you can cut it into 4. Quadsecting an angle is no problem. You cut it in half, you cut it in half again, you've cut an angle into 4ths. If you could do it into 6ths, then you could trisect it. Because it's easy to double an angle. You just take the angle and cut and do it again over here. Doubling an angle is easy. Having an angle is also easy. We just did it. It's not trivial. There's something to do, but we did it and took 3 seconds. The question is, how do we trisect an angle? So let me show you how to trisect an angle. I'm just going to extend this line. So I'm just going to pretend OA was already a line. Okay, that's a straight line. And step 1 is let's draw, again, as before, draw a circle with center O and radius OA. Exactly as we did before. This time I'll draw a semicircle. I won't draw the whole thing. I'll just draw a little bit of it. And let's call this point of intersection. Layla, you wanted to call it B. Let's call it B again. Okay, intersect at B. So again, the length OA is the same exact length as the length OB. OA is equal to OB because they're both radii of the circle. Does that make sense? Okay, step 2. Here's what I want you to do. You take your ruler and you hold it up to OB and you measure how far OB is. And then you're going to do something funny with it. So step 2 is mark the length of OB on your ruler and hold your ruler. Let me write this in English, not in chicken. And hold your ruler so that the end is on the line OA. Let me draw what I'm trying to say, and then I'll describe it. So here's what I want to have happen. I want to put a point somewhere here. I'm going to call this point, we have A, B. I'll call this point C. I'm going to make this point D, and I'm going to continue that line to B. And I want CD to be the same as OA and the same as OB. Okay, so here's what I'm doing. I mark the length of that radius on my ruler. Then I hold my ruler. I keep the end of the ruler on the line OA. I make sure that the length that I marked stays on the circle. And then I line it up so that the end of the ruler is passing through the point B. Does that make sense? So let me write that down. Let me zoom out just a little so we can see everything. So hold your ruler so that the end is on the line OA. This is at the point C. At the point C. The length that you marked, the marked length stays on the circle, and let's call that point D. Why can't I make this longer? I think I can. There we go. And so that's two things, but I still have degrees of freedom. I still have wiggle room there. I want that the end of the ruler passes through, if I extend that ruler, and the ruler passes through B, that original point B. Does everybody see what I did? You mark the length on your ruler, you keep the length on the line OA, you keep the marked point on the circle, and then you can adjust so that you go right through B at the end. So that's drawing this line CDB. So CD and B, then C, D, and B are collinear. They lie on a line. And the length CD is equal to the length OB is equal to the length OA because they were all the same by construction. Does that make sense? Everybody happy with that? My claim is that OCD, my claim is that OCD, let's call this angle beta. Let's call the angle OCD beta. And let's try to compute what beta is. Okay? Everybody with me? And the question is, so let the angle OCD equal beta. And the question is, what is beta? Allison. Well, because I marked it on the ruler. So I go to the ruler, I put my ruler up to OB. I put that length on the ruler, and I hold the tip of the pen on the line OA. I keep the mark on the circle. The circle has been drawn. And then the question is, what's that last angle? Yeah. Yeah, you mark it, and then you hold it up there. Does that make sense? And then just make sure it goes to the point B. So let me do one other thing. Let me draw the length OD. Oh, what's the length of OD? It's the same as all the other ones because it's still a radius of the circle. Okay. This is equal also to OD. I'll put vinculums on all of vinculi on all of these lengths. We do not know the length AB. DB we do not know. Yep, and it doesn't matter. What do you know about triangle C, about OCD? Let's check your OCD. What do you know about triangle OCD? Isosceles. So what if this angle is beta, what's this angle? Also beta. So what's left over if I go ODC, angle ODC measures how much? Lori. Exactly. We've got a beta there, a beta there. The three angles have to add up to 180. So this is 180 minus 2 beta. Say it again. Yeah, if you pull the 2 out, then it's 90 minus beta. It's twice 90 minus beta. Yeah, but we don't need to do any algebra with this. It's just 180 minus 2 beta. Does everybody see that? Amelia, you're happy with that? You're giving me a look. No, it's good. Because then the three angles will add up to 180 in the triangle ODC. Well, what does that tell us about this angle? ODB. This is 180. So let me mark it here. Let me mark it on the picture. This angle is 180 minus 2 beta. What must this angle be? This angle at D and this other angle at D have to add up to 180 degrees. This was 180 minus 2 beta. That has to add with 2 beta to make 180. Does everybody see that BDO is also 2 beta? You with me? Okay. What do we know about OBD? So let me write some of these things down. We started with, we got ODC. That tells us that BDO, this tells us that angle BDO is 2 beta. We're just angle chasing. That's all this is. We're chasing around the angles. This angle is 2 beta. What does that tell us about OBD? Yeah, please. Pretty please. Thank you. What does that tell us about angle? What did I say? OBD. OBD. It's also 2 beta. Why? Because this triangle is also isosceles. It's got OD is the same as OB. So this triangle is also isosceles. So this length here, this angle here rather, is also 2 beta. Everybody see that? So I've got 2 beta there. I've got 2 beta there. What is BOD? What's BOD? What's angle BOD? This was 2 beta. That tells us that angle BOD is 180 minus. We had a 2 beta there. We had a 2 beta there. So we have to subtract off 4 beta to get 180 degrees total. Everybody see that? 4 beta. Layla.
Does that make sense if they're the same from?
Well, they're not the same. So you mean OCD? That's a different triangle from DOB. They're not related to one another. These, maybe I drew them in a way that makes them look similar, but they're both isosceles, but the angles, this angle is 180 minus 2b, that angle is 180 minus 4b. No, there's no similarity. Does that make sense? So we've learned that this angle, we just said that that angle is 180 minus 4 beta. What about this angle plus that angle plus that angle? 180. Okay, so somebody's going to have to remind me, alpha plus 180 minus 4 beta plus beta has got to add up to 180. Everybody see that? Okay, so I'm going to write this down. Alpha plus 180 minus 4 beta plus, what was that last angle? Beta. And those three angles have to add up to a straight line, 180. Take a minute and solve this equation for alpha. Tell me what you get. You're getting 3 beta? Let's see. There's a 180 on this side and on that side. If I subtract the 180s, I'm left with nothing. Then there's minus 4 beta plus beta is a minus 3 beta. I'll move that to the other side. I get 3 beta. everybody get what Eleanor is getting? Wait a second. So beta is a third alpha, is alpha over 3. We did it, guys. Let's claim our prize. They said this was impossible. Something's wrong. Amelia. Notice what word I used. I said ruler. We don't have rulers. There's no such thing as mark this length. Let's go to GeoGebra. Let's do this construction in GeoGebra. Okay. So here we are. I'll just go somewhere else. Here's a new place. I have our original O and A, and here's some angle. Okay, so the first step is to draw the circle. Here's the circle. The next step is measure this length and stick it over here somehow. Where's the tool for that? It does not exist. It was not considered by the Greeks precise to be able to hold your finger on something as you try to wiggle it around. Everybody was confused at this step where we said, you know, wiggle this thing around and make the length CD somehow magically happen over here while going through the point B. It's not possible, Marley, and then Laura. That's the question. So this particular construction is not valid according to the rules of what construction means. There may be others. We have not ruled out the possibility that there's some other mechanism by which we can get that third angle, that 1/3 of an angle.
That like somehow the other side of the triangle using only compass. That is possible.
Yes. Yeah, we have to keep searching. Lori.
I assume I'm just misunderstanding this, but it feels quite simple to me. You just, because you could hold the compass at radius and then move it somewhere else. So you just have the compass set to the radius of the circle, and you just sort of, I guess you don't know on what point it would intersect.
So this is a really, really subtle and important point. We're going to talk about it more when we get to Euclid's elements, but Euclid's compass is a collapsible compass. It's a compass. If you think about the analogy to surveying, you put a stake in the ground, you walk some distance away, and you can make that circle. That's all that a compass can accomplish. Our compasses, we open them up. We have some fancy thing that we can lock that length, and then we move that length. And that's what you maybe were taught in school. It's actually not true that that's what you can do with a compass, according to Euclid. According to Euclid, the second you take that compass off the ground, it collapses, just falls apart. It's like the rope has nothing. Unless you had a stake in the ground and a length, you can't just move that length somewhere else. You can't measure that length and be sure that when you moved it somewhere else, you have exactly the same thing. Bless you. So your physical experience with a compass suggests possible moves. And I'll explain when we get to Euclid, I'll explain exactly why I can prove to you that his compass is collapsible. Because what he demonstrates is if you want to move a particular length to a particular location with straight edge and compass, you can do it. Which means, but there's a construction for how to do it, which means that, we'll talk about that in a week or something, that his compass collapses. So the problem here is I don't know where the point C is until I've placed it there such that it goes through this point B. It's the mystery of where these points C and D need to magically occur so that to make this construction possible. Okay, so people were inventing all kinds of instruments like a ruler. You guys just invented the instrument called a ruler where you can put a little tick and move that length, and then you can trisect. And people had other instruments that would square the circle, and they had other instruments that we're going to get to doubling a cube in just a second. Amelia. Yes. Yeah, that's what Euclid will allow you to do. So once you've drawn this angle, it's not that you have to construct that angle at the same location, but if you wanted to, you can move it to that location. There's a mechanism by which the angle at beta can be moved to the angle at O. The angle at C, the fact that beta, the angle is at C, you can move it to O. And we'll talk about that. That's not the issue. The issue is, can you actually construct this angle somewhere? And my claim to you is that no, you can't, but here we just did it. So we did it by cheating. And the cheating was that we marked the ruler where we're only allowed by Plato's rules to be using a straight edge with no markings. Okay, Lori.
But can't you like use the, can't you set a compass on O so that it also touches the other end of the semicircle, so it's set radius?
Here
And then,
or D?
yeah, well, D's not a set point yet, but
Exactly.
Then you just like. Sorry.
Yeah, yeah.
It seems really possible. But
It seems really possible. And for 2,000 years, everybody was like, wait, why can't you do it like this? Like 2,000 years went by. The fact that we can't solve it in the next 5 minutes, you know, this is what it feels like. We sit there and we try and we fail and we find, oh, but this is cheating because this was marking and this other tool doesn't really exist and so on. 2,000 years went by before people finally understood this problem. Like the fact that you guys are jumping in with potential solutions is exactly what you should be doing. It's what I want you to be doing, because that's what math feels like. I've sort of given away the ending. I've ruined it for you. There is no, there's a great article, maybe I'll link to it, called "When the Trisector Comes: What to Do When Someone Shows Up in Your Office." This happens from time to time. If you're a mathematician, people show up to your office and claim they have a proof of Fermat's last theorem or the Goldbach conjecture, or they figured out finally how to trisect. You know, all you idiots are wrong, and I know how to trisect, and you don't, and how to politely respond to that situation. Okay, are we happy with this attempt at a construction? And do we understand why it's not a real construction? It's the marking on the straight edge, which is why I always call it a straight edge as opposed to a ruler. People say, oh, it's a ruler and compass construction. No, it's a straight edge and compass construction. This move is not allowed. Layla.
But it's also that even if we did it with a ruler, it still wouldn't be possible.
No, it is possible. We just did it. Look, it's possible because you have a compass. Meaning you can measure the angle, and if the angle is 73, you divide 73 by 3, and then you draw that angle, right? It's not that the angle doesn't exist, and it's not that it can't be drawn. It's that the question is, can it be constructed by the rules of straight edge and compass? And the final answer is no. Amelia. So Plato like codified them. These are the rules we're going to play by. People made other rules. People played with this instrument. Archimedes played with something that will square a circle. One of the other games people played is let's invent new instruments that we can add to the game so that we can solve these problems. But so certainly the fact that you have a compass where you can measure a certain length and lock it and then draw a circle, that was absolutely motivated by this stuff. Protractor is just a way of measuring angles. I mean, any surveyor needs to know what an angle actually measures. Yeah, and rulers obviously want to be able to measure things. Like people invented all kinds of great tools to help them for practical applications. There's no practical application to this question. Anyone can trisect an angle because you measure it, you divide it by 3, and you draw a third of the angle. That's what any normal human being does. Mathematicians are not normal. We say, no, but can you do it with straight edge and compass?
So it's possible.
Exactly. So let me explain. Let's see. I want to stop in 5 minutes. Let me just explain what we talked about squaring. We talked about what squaring the circle means. We talked about what trisecting angle means. Let's talk about doubling a cube. So what is the problem of doubling a cube? And then we'll stop. This one I don't have too much to say on. What does it mean to double a cube? Double a cube. So if I take a 1 by 1 by 1 cube, so this is a 1 by 1 by 1 cube. If I double its side length, if I double its side, I'll get a 2 by 2 by 2 cube, 2 by 2 by 2 cube. And what has happened to the volume? The original volume was 1 by 1 by 1. The new volume is 8. The volume has been multiplied. The new volume is 8. So the original volume was multiplied by a factor of 8, also known as 2 cubed. And by the way, that's why this is cubed. This word cubed, the reason we call it 2 cubed is exactly because that's what happens when you grow a cube. Okay? And the question was, I don't want the volume to multiply by 8. I want the volume just to double. So the goal was, there was a king that was given a gold cube that was, 1 unit by 1 unit by 1 unit, and said, okay, give me one that's twice as big. And the mathematician said, yes, sir, and went home and said, wait, how do you actually do this? So our goal is to double the volume, not double the side length, just double the volume. And so, well, what is that? So if we have some length alpha by alpha by alpha, so that alpha times alpha times alpha all multiplies together to make 2, then what length are we trying to construct? The cube root of 2. The cube root of 2. Okay, so doubling the cube amounts to constructing the cube root of 2. Trisecting an angle amounts to trisecting an angle. We can talk about what that means in terms of a length that you need to be able to construct if you want to trisect an angle. So we're going to make an alpha by alpha by alpha cube whose volume is 2. So that's alpha cubed is equal to 2. So the cube root of that is just, the alpha is the cube root of 2. The king wants a cube with twice the volume. So if the original volume was 1, the new volume should be 2. And if I take the cube root of 2 times the cube root of 2 times the cube root of 2, I'll get 2. Does that make sense?
I thought the original volumes, I thought the original volumes too.
Oh, no, sorry. The original volume was 1, 1 by 1 by 1. We had a 1 by 1 by 1 cube in whatever units, and the goal was to double it. By the way, just the cube root of 2 also has significance since we spent a little bit of time talking about Pythagorean music theory. What's the cube root of 2? Total aside. What is the cube root of 2 as an interval? Anybody know? Remember, in equal temperament, every semitone is 2 to the 1/12. It's the 12th root of 2. And so the cube root is the 12th root raised to what power? This is 2 to the 1/3. 1/3 is how many twelfths? 4 twelfths? What's 4 semitones? C to C sharp, to D sharp, to E. 2 full tones. Yeah, it's a major third. So this interval, musical interval, just so you know, the musical interval we're interested in is a C to an E, or a major third. A major third. So when you hear a major third on a piano, it's not the perfect third that we talked about a long time ago. It's this cube root of 2 interval. And if you do 2 cube root of 2, if you go from C to an E, what's the major third above an E? G sharp. G sharp is the third in the E scale. Same thing as A flat. And if you go a major third above an A flat, in the A flat scale, A flat, B flat, C. So this makes the C to E to G sharp is an augmented chord. Okay, just as an aside, augmented chord. So we're trying to construct an augmented chord in music theory. All right. We talked about the three impossibility problems in antiquity. Let's take it all the way back to the Babylonians. We have a very, very special guest here today. Pavla Rosenstein is visiting us from Yale University, from the Yale Babylon collection. She's a PhD student in Assyriology. She has an undergraduate degree from Cambridge and a master's from University College, University of London. University of London. Please welcome Pavla. Oh, yeah, take it away.
Thank you, Alex. Good to meet everyone. Yeah, my name is Pavla. So I'm a PhD candidate at Yale. My dissertation is actually not on mathematics at all. It's on the early Mesopotamian law collection. So who's heard of Hammurabi? Amazing. Who'd like to summarize quickly who Hammurabi was for those who haven't heard of him? Anyone? So Hammurabi stele is a collection of laws, some of which you may have heard of, that were very similarly structured in the Bible, for example. So tooth for a tooth, eye for an eye. So that's what I study, but I also work at the Yale Babylonian collection. And the Yale Babylonian collection is the largest collection of cuneiform artifacts in North America. There are about 40,000 of them. Most of them are inscribed in cuneiform. So does everyone know what cuneiform is? If I talk about the cuneiform writing system, does anyone know what cuneiform means? Yeah.
It's like wedges or reeds.
Yeah, it comes from Latin cuneus, which means wedge, and the writing is very wedge-shaped. We'll see a lot of it as we go on. And some of those tablets are mathematics tablets. So you already looked at the tablet that shows an awareness of the square root of 2, which is one of them, and we'll look at some more. But first, we're going to go all the way to the beginning and chart the history of counting that gives way to accounting, which gives way to recorded mathematical problems and solutions, which gets us then to that square root of 2 tablet that you guys talked about earlier. So first, I'd like you to, well, actually, first, let's just make sure we orient ourselves. So when we talk about cuneiform and Mesopotamia, we're essentially talking about what today is much of the Middle East. So most of it is Iraq. This is the Persian Gulf, or Arabian Gulf. And this is where some of the earliest, what we would call civilizations, took place. So some of the earliest cities and crucially, the earliest written artifacts have been discovered. So when we talk about written artifacts, we mean artifacts that not only have pictograms, where you have a picture that represents an idea or a concrete object, but also elements of grammar and replicable systems of writing that can be translated between language and language. So the cuneiform writing system is a system like the Latin alphabet, for example, and it has a number of languages inscribed in it, including Sumerian, which is the oldest attested written language, a language isolate, so not related to any others, and Akkadian language, which is a Semitic language, which is related to Arabic and Hebrew today. And in terms of the time period, the first cities emerged in the, well, it's debatable, but the first cities that also yielded written artifacts emerged in the 4th millennium, and the first written clay tablets with cuneiform or proto-cuneiform symbols on it emerged towards the end of the 4th millennium. So that's where we are. And I'd like you to imagine a scenario where you might have a flock of sheep, for example, and you want to sell that flock of sheep or send that flock of sheep to someone else far away, and that person is going to receive a particular number of sheep. How do you make sure that none of the sheep gets stolen along the way, and the person who receives the sheep has a contract or a record of how many sheep you sent? Any ideas about what you might do? And the clue is in the picture.
Don't be shy. Throw out ideas.
Throw it, yes.
That represents X number of sheep, and then put however many objects, or like send the objects.
Exactly. Yeah. you will have an object that will represent, say, 1 sheep or 10 sheep or any number of sheep, and you will send it along with the sheep. So in this picture, this is an example of these objects. They're called tokens. So this is actually a replica. This is not clay antique objects. And they would be put in something called a bulla, which is a sort of an envelope. And then later, they would also be signed. So you would have some kind of a mechanism where you would say, okay, I, person A, really have put these tokens in here so that you, person B, know how many I've put in. And one of the ways to do that was to roll a cylinder seal. So this actually is an antique cylinder seal, and you would roll it out on the outside of this bulla, and then impress the objects that were going into it on the outside as well. So when you receive that bulla, it would say on the outside, okay, there are supposed to be fatty sheep in it. You could crack it open, see that there really are tokens representing fatty sheep, and everything would be okay. So this started happening, we think, around 9,000 years before present, and went on for millennia, and actually continued to be used even as later mechanisms for recording these sorts of numbers came into place, like tablets and writing. So this is an example, a very early example, where you have 3 tokens down here, which each stand for a flock of sheep, possibly 10 sheep each, though this is very, very difficult to prove. And then these cones would represent small measures of grain. And then you can see they've made these marks. You have the 3 lentils here, and then the 3 bits of grain here in the bulla, in the envelope, and then that would be sent. So at some point, there was a very significant innovation that took place, which was that people realized you don't really need the objects, you just need the symbols representing the objects. And the little tablet on the right represents that innovation. So now you have 2 dots and 2 kind of wedge-like impressions just on a piece of clay. So we move from a very concrete representation of numbers to a more abstract one. And this is happening in the 4th millennium BCE, and very soon afterwards, within a matter of a few hundreds of years, we start getting the first tablets which have writing on them.
So there's already an abstraction from here's a sheep to there's a little ball inside, hidden inside a seal, to I'm gonna have some error correction that on the outside I'll tell you how many, if you don't want to crack this open, I'll tell you how many there should be inside. To don't worry about what's inside, we don't need an inside, it's just the impression, the imprint is enough to tell you what the representation is of that sheep. So it's like a second layer of abstraction from
Exactly.
the actual sheep.
Yes. And in hindsight, that seems very obvious, right, to us, because we're so used to dealing with many, many levels of abstraction that have been developed over millennia. But at the time, this was a very revolutionary, very significant step. By the way we use envelopes is also connected to this. There is a theory, so a bulla that you see on the left here was a round object, and you would kind of roll it to see everything that was on it. Later on, we have rectangular tablets, which have cuneiform writing on them, but the way you read them isn't like a book. You don't go like this, you go like that. And that is theoretically connected to using the bulla. So that there are all of these kind of connections and developments and evolutions where writing and counting and communication and trade and commerce are connected. Okay, so here we have the next step in that sort of evolution. So this is from a city, ancient city called Uruk, which was in southern Mesopotamia, so southern Iraq today. And you can follow quite easily. So here we have the physical objects. Oops. We have the physical objects. We have their impressions on the bulla, which would contain the objects inside. Then the next step in the evolution is we have the impressions of those objects on a piece of clay. And here we have a more systemized way of doing that. So at this point, we don't see impressions of physical objects. We see those impressions made in an abstract way to represent those objects with a stylus. So at this point, the tablets become rectangular rather than circular, which actually mimics architectural evolution as well. So that at some point we have circular buildings and then they become rectangular. So it's an interesting kind of connection in terms of shape. And the stylus would be a reed, a cane reed, and the tablets would be made from mud, from riverbanks, and you would start impressing numbers on there. So because the stylus was, or the reed was circular, these very early tablets usually have circular marks or marks that can be made with a circular reed that kind of have, you know, they look like semicircles. Later on, the reeds are cut so that you have a triangular piece of reed, and that's what makes the wedge shapes that we see in cuneiform later on, and that's what gives it its name. So let's just make sure we understand this. So these two circular symbols represent the number 10, and these wedge-like semicircles represent the number 1. So we have 24 units, and we know from other texts that this was likely a symbol that represented textiles. So what we're likely seeing here is a very early trading document. And again, we have this connection between writing, counting, trade, and commerce. Are there any questions at this point? Okay, I'll carry on.
It's clear that you make circles by pushing straight down and the ones by pushing horizontally.
Mm-hmm. And we'll see later the cuneiform signs for 10 and 1 follow on from these shapes. We also see here a decimal system potentially, but that wasn't the only system that was used. And we'll look at that later. Okay, so this is about 100 years later, and we see the next step in the evolution, where we continue to have the round stylus impressions, but the symbols for the commodities or other linguistic or abstractions of concrete items become more developed and become more complicated and complex. So using what we learned here, that this is 10 and this is 1, let's see if we can figure out what's going on this tablet. So the top, oh no, I've ruined it. You didn't see anything. So the top image is the front of the tablet, then you would turn it over, and the below image is the back of it, or what we call the reverse. And this is a hand copy of this photographs. It is a little broken at the top, but we can assume that we see everything that's on there. So it's 2 circular dots, and then 1, 2, 3, 4, 5. So 2 10s and 5 1s, yes. And then 1, 2, 3, 4, 5. And then here we have 3 dots. So who would like to guess what's going on here?
Form of addition.
Yeah. Exactly. Yeah. So this is what we have. So we have 2 10s and 5 units. This symbol means a nanny goat, so a female goat. And here we have 5 units for a male goat. And remember the sign. So this is a sign that's later called mash-2. It means a male goat. So just imprint that into your memory. And then we have a name. And these sort of very early cuneiform tablets are very difficult to interpret, and we don't really know what this name means. And then at the on the other side, we have 30, so 25 plus 5. And this symbol can mean small cattle, can also sometimes mean sheep. And yeah, so you can follow the system. There are a number of different systems. Also, by the way, hang on. Let's see if I know. So Denise Schmand-Basserat, and you can learn more about her work here. She was one of the scholars who studied these tokens very intensely from a perspective of art history as well as history and Assyriology. And she had a theory that some of those tokens then turned up later in cuneiform signs. So this particular symbol here, interpreted as small cattle or livestock, is also frequently found as a token earlier. And later on, it can mean a sort of a similar sign, which is a square with a cross in it, can refer to sheep or livestock as well. So these are theories, but you can definitely see a lot of connections and evolutions through kind of the token system, and then the more abstract system of counting, and then cuneiform writing system later. Okay, so these are some examples. I don't know how easily. Oh yeah.
Oh, sorry, I was this, if this is off topic, please keep coming, but I was just curious, how did they find out that that symbol meant like a goat? Like, what?
It's a complicated process, and the further back you go, the more difficult it is. So this is a little bit of a different topic about decipherment of cuneiform altogether. It started first by translating Akkadian, which was on a trilingual inscription called the Behistun inscription, which was a sort of a Rosetta Stone monument for cuneiform languages. And because Akkadian is a Semitic language, that was reconstructed first. Very, very briefly, there are a lot of bilingual lists called lexical lists, which are an example of sort of early dictionaries or lists of words that translate between Akkadian and Sumerian. So that's how Sumerian was deciphered. And then Sumerian was following this sort of proto-cuneiform precursor to Sumerian, which had a lot of similar visual markers to logograms used in Sumerian. So from that, we were able to decipher some of these early proto-cuneiform symbols, but a lot of it is debated, and there is a joke in Assyriology that there are as many Sumerian grammars as there are Sumerologists. So bear that in mind.
Can I ask a really stupid question? With the advent of AI, have you returned to these questions and seen if those systems can suggest other patterns that give us 10 more Sumerian grammars? That's
a really good question. There is a lot of AI work going on right now, mainly connecting fragments of texts, because there are up of 1 million of cuneiform artifacts. A lot of them are broken up. A lot of them are copies. So, for example, literary texts may be attested in lots of different copies from school exercises, or canonical copies that were found in libraries, quote unquote. So that is mostly what it's being used for at the moment, but there's a lot of interesting work going on in there, and maybe I can send some links at the end. Okay, back to 3000 BCE, 4th millennium. So there has been a lot of work done on these very initial proto-cuneiform and early cuneiform tablets and the counting systems they used. So Alex already talked to you about the sexagesimal system, mainly used in the Old Babylonian period, but that wasn't the only system used. And this is just an example of it, and I can include a reference for this book, which explains these systems very, very nicely. But you would have sexagesimal systems, you would have bisexagenal systems, you would have decimal systems, and they would be used to count different things. So people, for example, were counted using a different system than grain amounts or liquid amounts, or for measuring time, for example. So this is a very nice one, because this symbol basically represents a sort of sun setting, or it kind of represents a day. And then you can see, you have the unit of 1 that we've seen before, that's 1 day. Then you have the unit of 10 that we've seen before for 10 days. Then you have 1 month, and they were very economical and efficient with the symbols, because there's only so many symbols you can make with round stylus by turning them around or making them bigger or smaller to represent different things. So again, you have this jump from 1 to 10 using the circle, and you have 10 months, and then 1 year is its own symbol. Not necessarily. So you may be, for example, counting rations to feed a number of people, or you may be counting the number of inhabitants, soldiers. Yeah, there were a lot of different ways of, and again, you have this connection between counting and writing, and a lot of the early writing was essentially mathematics and accounting. And by the way, this is borrowed from a lecturer at Yale, Klaus Wagensonner, who does these really brilliant classes on the origins of writing, and mathematics as well. So this is visible? Yeah. So this is an early cuneiform symbol for counting, but it also means an accountant or a scribe. So again, there's this connection between counting and writing. And this is the Chinese symbol Suan 4, which means to calculate. So there's also an interesting pattern that I think, Alex, you mentioned as well about different civilizations and different groups of people around the world kind of attacking some of these problems and coming up with similar solutions at the same time or independently or at different periods. Okay, a little.
On the topic of measuring things with different units, depending on what they are, we continue to do this.
Exactly. Yeah. Yeah.
Versus liters versus.
Exactly. Yeah. And I think I detected a British accent somewhere earlier, but right. But I remember a time when we had shillings, and you know, and of course the imperial system is very different to the metric system. So we do exactly the same thing and we translate all the time. So it's not, yeah, it's not unusual.
Last places still use the imperial.
The US, yeah. So apparently in the 70s, there was a federal law passed that introduced the metric system, but it was to be taken up voluntarily state by state and no one did it. So a little bit of a detour just to really solidify the connection between trade and counting and writing. This tablet is a cuneiform tablet, which looks a little bit more like what you might expect if you've seen cuneiform tablets before. It's from a little bit later. It's from the Ur-3 period, which was in the late 3rd millennium. So this is about 1,000 years after the first proto-cuneiform tablets. And it is a theoretical model for what would happen if you received a male cow and a female cow, so a cow and a bull, and what number of livestock you would have after several years and what amounts of dairy they would produce. So you can sort of follow this. We'll just do a couple of lines. So these wedges now, remember we had the kind of line-esque semicircle that represented 1. This is not so dissimilar, right? So this is a vertical wedge. Now we use the triangular bit of a reed to inscribe it. So this each represents 1. So it's 1, 2, 3, 4, 5, 6, 7. So we have 7. This symbol represents a cow. So we have a cow, and this just means that it's fully grown. So and then here we have 1 cow that is 3 years old. So here we have 1, 2, 3. So again, we have a slightly different system for measuring age as opposed to units. And here we have 1 cow that is 2 years old and 1 cow that is 1 year old. So this is, I think, year 4 in that tablet. And what that tablet essentially does is introduce, this is one of the earliest examples we have of something that we would call compound interest. So the idea that you will start with 1 of something and that 1 will grow, or 2 of something and that 2 will grow over time and compound and compound and compound. And interestingly, the word for interest in Akkadian is tsiptum, and the Sumerian logogram to represent that. So logogram is, we use logograms today as well. So you might write out $2, or you might, do the S sign with 2, and the S sign is a logogram. So that was very common in cuneiform sources, and often the Akkadian words would be written out or would have a Sumerian logogram to capture the essence of it. So does this, I asked you to remember a sign before, does this look familiar? Male goat, yeah. So there is this connection, and again, a lot of this is suggestive as opposed to necessarily always proven beyond any doubt. But there's a suggestion between trade, compound interest, growth, livestock, and so forth. And one of my professors always says that if you wanted to be rich in Mesopotamia, you should get a lot of sheep because they really paid well. Okay, so that is sort of a whirlwind overview of the very early mathematical systems of counting, compound interest and growth and accounting. So we'll move on to the Old Babylonian period. This just shows you the evolution of the cuneiform script. So this is kind of how it began. Very pictographic, very close to a concrete representation of objects. The pictograms, represent the objects that they're supposed to depict. And it gets more and more abstract and more uniform and becomes more like a typeface or a font that we recognize as lines of writing. And that takes us to the Old Babylonian period. So that is early second millennium. So a little bit more than 1,000 years since the first proto-cuneiform tablets. And at this point, what happens in Mesopotamian history is at the end of the third millennium, you had, during the Ur-3 period, where the compound interest tablet is from, you had quite a centralized state called Ur, well, based around the city of Ur. That falls apart, and what happens afterwards is a lot of fragmentation, and you have smaller entities vying for power. A lot of things become, to use an anachronistic term, kind of less centralized and more privatized. And it's in this environment that we see a lot of scribal training in small private dwellings. And it's in this context that we find a lot of the mathematical tablets, and they all appear to be math exercises that would have been used to train scribes. So again, mathematics, accounting, and writing was taught kind of in the same way. The sexagesimal system is now very dominant, though not unique. And we have these even more abstract symbols now that are made with the triangular stylus. So the vertical wedge is used for units of 1 to 9 or 60. So depending where it is. Then this is called a Winkelhaken, a German word for just when you go like this, as opposed to vertically or horizontally, that represents 10. So here we have 1, 2, 3, 4, 5. So 50 tenths, 50, and 9 units. So that's a number 59. If we go past the decimal space, so we have a half here, which very kind of logically is a process things in half. So that's 0.5. Here we have six units. Then we have 1, 2, 3, 4, 5 60s, and 1, 2, 3, sorry, 5 10s, and 1, 2, 3, 4, 5, 6 60s, which together, wait, I've now lost myself. Makes 416.5. So I think you've already covered this as well, but what else do we use sexagesimal systems for today? Time and sorry, the year, yeah, and we've just done it on the board. Yes, yeah, exactly. And I've learned recently that there is a computer programming language that uses sexagesimal systems as well, and it's caused some issues with translating it. So there's more. So this is an example of where a lot of the mathematical tablets were found. You would have a room, and some of them were found actually as floor fillers. So a lot of them would be discarded and reused, because remember, this is all done on clay, and clay can still be reused as building material. And we have in this is a city of Nippur, where we have a lot of these scribal tablets from, I think about 127 tablets, yeah, just from this house alone. And you guys have covered this as well, but maybe you've got your midterm coming up, right? So who'd like to quickly just give a very brief summary of what this tablet represents and why it's important? Now I feel like I'm picking on you. Sorry. Yeah.
You spoke about how it's, I mean, it looks diagonal, but it is a square.
Mm-hmm.
And how the numbers in the middle use the sexagesimal system, and there's an implied decimal after the 1. And it denotes the square root of 2. And the assignment for the student was trying to find the hypotenuse of a unit triangle if the triangle was only, if each side was only 1/2.
So
Actually, okay. Yeah, that's not necessarily what the assignment was. I'm curious to hear what Pablo would say, but one interpret, so along the main diagonal is the square root of 2, and then on the side, we have the 1/2, the 30, and then below the square root of 2 is root 2 over 2.
right. Yeah. So a way to figure out the diagonal with a constant for the square root of 2. And this number represents the constant. It's a very, very close approximation. And that number is also, so there are other exercises that are just lists of constants and also lists of reciprocals. So we know that number was used in these lists and was known. So it's not just a guess. We have references that kind of show that was an awareness of what it meant as well.
And curiously, Pablo's slide has root 2 times 30. So maybe that 30 wasn't a half, but was really 30. In which case, that is, again, the right, it would be square root of 2 times 30 for the diagonal instead of just root 2 over 2. Whether you interpret 30 as a half or as 30 itself.
Right. And that's the fun with the sexagesimal system, because it can, 30 can always be half of 1 or 30 or 30 over 60. Okay, so very unceremoniously wrapped, but I have a little show and tell. So this is a 3D print of the cuneiform tablets from Nepal. So this is housed at the Babylonian collection, was scanned and 3D printed out, so you get a sense of how big these tablets were. And these circular ones are called lentil tablets, and they're associated with scribal education. So this is before the scribes learn how to shape the rectangle properly. And if you think it's easy to shape a rectangle out of clay, it's not. It's actually pretty hard. So doing it as a circle is kind of more elementary. And what we see on this tablet is an awareness of figuring out the relationship between the area pi, or an approximation of pi, and the circumference. So once again, I don't know how well you can see. Can you see there are 3 wedges here? Okay, so who would like to volunteer and answer for how many, what number is represented here on the right? You can do it. 9, yeah. What about here? This is harder. That's a 5, yeah. So it's actually 4. 1, 2, 3, 4. So 4 of Winkelhaken wedges and 5 of vertical wedges. What does that give us? Exactly. Very good. Okay, so guys are brilliant. Giving it away a little bit, but have a look. Who'd like to volunteer kind of what calculation is going on here? Yeah. Exactly, yeah. So 3 is here used as an approximation of pi. And you've probably learned pi squared in school, but there's another way of doing it, which is calculating the circumference squared divided by 4 pi. So we have 3 as the approximation of pi. We have the circumference, 3 is the circumference. We have that squared to 9, and that gives squared divided by 12, which is 4 pi, gives 45, right? Is that correct? I always get lost with the math calculations. But essentially, that's correct, right?
Yeah.
Yeah.
Square of that is 9. That's the 3 is up top, the 9 is to the side. And then you're supposed to divide it by 12, according to this process, to figure out what the area is. Circumference squared over 12, using pi equals 3 as an approximation.
Yeah.
So then 9/12 is 3/4. And if you're going to write that in base 60, how much is 3/4 of an hour?
45.
45 minutes.
Yeah.
So there's your 45, Elisa.
I understood it that did they do that the 9 on, maybe this is what you said, I didn't understand, that the 9 on the right is the circumference, meaning that they, like, why do they have those 9 wedges is an indication of the circumference, and then 3.
I think the interpretation is the 3 is meant to be the circumference.
Yeah.
Then there's a side calculation for the 9.
Yeah.
It's off to the side somewhere. You got to work out what 3 times 3 is.
And well, why are there those 9 wedges?
3 times 3. So 3 squared,
Each side
yeah.
is a 45, which is 9 divided by 12 is 3/4. 3/4 in base 60 is 45/60.
Yeah. exactly right. And there's an Assyriologist called Eleanor Robson, who's written quite a bit about the history of mathematics. And she makes the argument that all of the sort of thinking behind this was always thinking of the circle as what's inside the circumference, as opposed to a function of a radius. And there are a lot of other, how much time have we got? Am I running out?
Finish up.
Okay, all right. So there are lots of other exercises that try and figure out areas of things. This is another quick example. So the task here is to figure out this area minus this little area inside. And there are two methods that are shown here. One is by subtracting the smaller area of the smaller square from the bigger one. And the other is by dividing the biggest square into 4 rectangles and then multiplying the area of each rectangle, of one of the small rectangles, by 4. Couple of other examples, isosceles triangles, so you can compare that to the earlier exercise, but this is a way to try and figure out different areas of divided isosceles triangles like this. And there are actually 2 theories. One is that because the calculations work in an approximate way, so one theory is that this was meant to be an approximation, and another theory is that it wasn't actually a triangle, but this shape with a triangle cut out of it to figure it out. Okay, one final example. So in the Scribble curriculum, the students move from doing very quick arithmetic to then figuring out geometry, and then they would have applied mathematics that would be applied to trade and commerce again. So this is a tablet where you have a lot of different exercises, which are always kind of saying, you have this problem and this is the solution you come up with. So here, the example is you have 300 liters of oil. You buy it at a particular rate of shekel per amount, and you're going to sell it for more, and you have to figure out the profit. So you can do that at home, but it works. And that's it. I've included a few references here, and I don't know if we have time for questions, but I hope there's a